So the next problem, it is a problem about an attempt to stop a proton. So let's assume that you have a proton, right, which moves fast. Initial velocity is very large, right? Let's say 2 times 10 to the power of 6. I will write it. Right? And let's say this proton flies away from this surface, from this plane, right? So this way. And we want to stop it. We want to stop it. And this plate, this infinitely large charged plane, are going to be negatively charged. Right? Negatively charged, of course, there will be force of attraction acting on this proton. As a result, proton will fly for some short distance. It will stop for a moment, and it will start moving backward. Right? So we need to find this distance from the plate, from the initial point of the proton to the turning point. Right? So that's what we need to find. Okay, so now let me sketch this situation, physical situation, and then we'll start discussing what can be done to solve this problem. Yeah, so this is problem 23, 29. So from chapter 23, problem 29. So this plate, infinitely large, charged plate is negatively charged, right? And so let me draw first electric field line. So this plane, of course, create a uniform electric field. And let me draw. So these, right? And of course, over here, exactly the same story. Right? So the electric field lines, you remember, they start on positive charges and end on negative charges. So they end on the negative charge, on these negative charges. So next, of course, our proton, initial position. Initially, it is position over here. It's a positively charged, Q, and initial velocity this way, right? V naught. Okay, so I can write down initial velocity. Yeah, it's a 2 times 10 to the power of 6. So I can write immediately so that the initial velocity V naught is 2 times 10 to the power of 6 meters per second. So initial velocity of this proton. And of course, yeah, it will be traveling this way, decelerating. We will get that deceleration mathematically. It will be traveling this way, and at a certain point, it will stop for a moment, and it will start moving backward, right? So this is a turning point, so we can tell immediately that velocity at this point is 0 at that moment. So let me write that V final will be 0. It's a turning point. Turning point at the turning point. Then what else? Yeah, we need to introduce coordinate system because we're going to deal with vectors, directions. It makes sense, of course, to introduce coordinate system. I will draw it here underneath. So this will be my x. Right? So then I will position origin at the place where where we have our negatively charged plane. So x equals 0. So that's my x equals 0. And what do we have to find? We need to find this final position, right? This x. That's what we need to find, right? So that's our question. Right? That's our question. That's what we need to find. Right, so I can also, as a result, write down that the initial position of the proton is 0, because that's where I position my origin, so I can write that down. X not equals 0. What else can I add? Finally, what do I have to find? Let me write that down. So find x, right? So turning point. Again, that is the turning. That's what we need to find. Let me check if I mentioned everything that we need to that I have to show you. Yeah, that's it. Yeah, and surface charge density is given of this plate. Let me just show that we have here surface charge density. Okay, so now we need to discuss the strategy of this problem, or at least create a train of thoughts which which we have to follow in order to solve this problem. Right. So first, if you ignore the nature of the force, we know that the nature of the force acting on this proton and decelerating it is an electric force. But if you forget that that is an electric force, this is effectively physics 1 problem. We solved plenty of problems of this type in the previous semester in physics 1 when we had some force acting on some object, that object accelerated or decelerated, we would have to find velocities or position or time. We had plenty of problems like this, right? So effectively it's a physics 1 problem. And of course, since we want to describe motion of this object with mass m, description of motion, that's what Newton's second law does. This universal law, which is capable of describing motion of any mechanical system at any moment of time, at any point of the universe. Okay, so of course we will be using Newton's second law to find an acceleration. And Newton's second law basically takes us from the world of forces to the world of kinematics. And of course it takes us to the acceleration. And once you know acceleration, and if that acceleration is constant, you can use kinematic equations, and you can use any kinematic parameters from the world of kinematics. You can find position, you can find velocity, you can find travel time, anything you want, right? Okay, so now let me, after all this, let me create sort of like a train of thoughts to solve this problem. So I will start from the very end. Eventually we will have to find position x. In order to find this x, we will need to know acceleration, right? And this transition from this point to that point, of course, can be done using kinematic equations, right? If acceleration is constant. So let me write, so here I will use kinematic equations. Which kinematic equations we will discuss when we get to that point. Okay, so that's the last step. Then, before this step, of course, in order to find acceleration, of course, we need to know force. And of course, force in this case is an electrical force, right? And which law allows us to make this transition? Of course, Newton's second law. I will write F equals ma. Right? So then, in order to find force, electrical force acting on the charge Q, right? So we need to know the electric field, which is created by this infinitely large plane, and expression which relates force and the electric field, F equals QE. So that's basically the steps which we have to make to solve this problem. Okay, let me frame this strategic direction of our solution, right? And so now we need to start looking at the details. Right? So again, I will start with the electric field, then make transition to this, then that, and then finally we will find position. So let's start with electric field created by this infinitely large charged plate. We derived a couple of classes ago the expression for the electric field created by the plane. It's a surface charge density divided by 2 epsilon naught. Okay, and we see the direction. You see direction of the electric field. Okay, I forgot to label. Right, so this is our electric field. Red one. And you see it points in the negative x direction, positive x direction that way, electric field is in the opposite direction. So I will put absolute value of the surface charge density, because our surface charge density is negative. I just want to drop this minus and show the direction with the minus next to the unit vector. Eta divided by 2 epsilon naught, and it is in the minus I hat direction. Right. Okay, so that's the electric field. Of course, uniform electric field created by this plane. Okay, so we are over here. Now we need to use this expression to get electric force. So from here, electric force will be Q times E. Charge is positive, so no troubles from here, so we're not going to get any minuses, right, like in the case of an electron, if we had an electron. Alright, so it will be just this multiplied by Q. Q eta hat, eta, absolute value, divided by 2 epsilon naught, and in the minus I hat direction. So force acting on this proton acts in the negative x direction, so that way, which makes sense because the force between this negatively charged plate and the positively charged particle, of course, the force of attraction. So of course, force acting on the proton must be in the negative x direction, and that's what we got mathematically. Now we are here. Now we need to apply Newton's second law, of course, to make this transition from this point to that point. Now, Newton's second law, of course, F electrical equals mass times acceleration, right? So from here we can get acceleration immediately by just dividing this expression by mass. So I will get acceleration equal F electric divided by m. So I'll just rewrite this expression with mass downstairs. So it will be Q, absolute value of eta, divided by 2 m epsilon naught, and it is in the minus x direction. This is I hat. In acceleration, our acceleration now is negative, right? So it means acceleration points in the negative x direction, which is actually deceleration. It decelerates this proton, right? Of course, first initial velocity is very large, and of course, eventually, after significant amount of deceleration, velocity will be 0. So now we are here, and now we have to make the last step. Before we make this last step, of course, we have to check if our acceleration is constant. And it is. You see, Q is constant, this is constant, all this constant, right? So I can write this is constant. So as a result, it's legitimate to use kinematic equations. So we can use kinematic equations. So the question is, which kinematic equation can be used? We had 3 of them, right? Since there is no any time information, and since the question is not about finding time, it's a direct indication, so that we will have to use the last equation, the no time equation. Right? So let me use that equation. Let me write that down. Write that equation down. All right. So it will be v squared equals v naught squared plus 2a x minus x naught. So that is a no time equation, and let's simplify it, because what? Final velocity at the turning point is 0. So let me dump this term. Then initial position of the proton x naught also 0. So let me dump this. And yeah, the rest are not 0. And don't forget that our acceleration is negative. I will take this minus, right? I will take this minus and I will use here. So then initial velocity given, acceleration we've basically found. You can actually calculate. You can get the number, but I'm not going to get it. And that is our unknown. That's our x. That's what we need to find. So let's just solve it. So we have only one unknown. So we have to solve it for x. First, I will move this term to this side in small steps. So minus v naught squared equals to 2a times x. Okay, so we can solve it for x. So from here, x will be equal to minus v naught squared divided by 2a. Again, don't worry about this minus, because this minus will disappear since acceleration is negative. This minus will come from acceleration, canceling that minus. So it will be minus v naught squared divided by 2, and our acceleration, which we just found, q absolute value of eta divided by 2 m epsilon naught. Minus. I was talking about minus. Okay, here is minus. So this minus and that minus, they cancel each other. Then 2 factor of 2 here and factor of 2 there also, they cancel each other. And finally, we have an expression which we want to find. So it's m epsilon naught v naught squared divided by q and the absolute value of our surface charge density. So that's our x. Everything is given. Mass of the proton, you can find it in the book, right? I wrote it down. Universal constant, you can open up and look at the book. Initial velocity is given, a charge is given, surface charge density is also given. So if you plug numbers, you will get this answer. I will just write down the answer. You will get 0.18 meters. So that's the distance that this proton will travels to this turning point. This is the turning point. 18 centimeters, right? 18 centimeters. Thank you.